Hello everybody, my name is Deppe. I work at the Walther-Meißner-Institute, which is located in Garching on the campus of the Technical University of Munich. We are also part of the Munich Excellence Cluster, Munich Center for Quantum Science and Technology, MCQST. And today I want to take you along with me on a tour through my labs. Please follow me. Welcome to Alice Lab. Here we are working on quantum microwave communication between superconducting quantum processors, and our research is now to address the next question: how to connect such superconducting chips or superconducting quantum computers with each other with a quantum LAN. And you can imagine such a quantum LAN similar to a classical local area network you have in your office, where you connect two or more computers with some classical network cable. You use microwave frequencies for this, and in our case we also use microwave frequencies to connect the superconducting quantum circuits or quantum processors. Let's dive into the details and move on to the experiment itself. So, the experiment is always performed at cryogenic temperatures of roughly 50 millikelvins. These are 500th of a degree above the absolute 0 point. The reason is that we are working with not only with microwaves, but we are working with quantum microwaves. And although they work at the same frequency as your standard microwave oven at home in your kitchen, the power is approximately 20 orders of magnitudes less than that. So this is a 10 with a 1 with 20 zeros in it. Yeah, that's the difference in power. So these signals are very fragile, and in order to shield them from environmental noise, we have to work at such low temperatures. And to achieve these temperatures, we need to use elaborate cooling machines, so-called dilution refrigerators, and here you see one of them. In a dilution refrigerator, you have an operation in practice, not from the principle, but in practice, very similar to your kitchen refrigerator. So you open the door. In our case, the door is already open because we can access the cryostat now. Then you put in your food. In our case, we use our experiment, and then you close it and wait for a while, and then it will get cold. And in this particular case, the cooling technology starts from here, room temperature, and slowly goes down via some pre-cooling mechanisms to roughly 50 Kelvin, 4 Kelvin, 1 to 1.5 Kelvin, 700 millikelvin, 100 millikelvin, and here below 50 millikelvin. And this is where our experiments are mounted. And in fact, all this part here and even some of these parts on top of these plates belong to our experiment. Our experiment is now to do a proof of principle experiment on, or to do a proof of principle on how to achieve such a future quantum LAN architecture. And we choose the so-called teleportation. This means we want to teleport, very similar to the way you would envision in Star Trek, a state of light. So we don't teleport people, we teleport a state of light from one of these fridges here through our quantum LAN cable here into another fridge in a different lab, which you will see a little bit later. So here you see these boxes, and in these boxes, aluminum boxes, these are just shielding boxes, we generate the quantum states. So if you would compare our experiment to a quantum computer, the complexity would be that of a 4 to 5 qubit experiment. So it's already pretty complex. All information which needs to be transferred from Alice to Bob's side. So this includes the pre-shared entanglement state, but also the classical communication has to go via our quantum local area network or quantum LAN cable. This you see here, and it's one of the at the heart of our setup. You see here the three ends of superconducting coaxial cables. In these cables, the actual states are transferred to Bob's side. Superconducting cables are being used because they have extremely low losses comparable to optical fibers. These are on the order of 2 dB per kilometers only. So 7-meter distance, our current distance between Alice and Bob, is negligibly short. You see that the cable or the superconducting cables are inside some shielding tubes. These are there for cryogenic reasons. Here we have 1, 2, 3, 4, 5 of them, and they are used to shield the cables from the thermal radiation from room temperature, because also our cables in our experiments should operate at 50 millikelvin, just like our actual experiment. Next, I want to show you some details of how Alice looks, or Alice part of the setup looks inside these aluminum boxes in our actual experiment. And for this reason, I want to ask you to follow me to this little table here where I've prepared the boxes for you. So you see here I have one of these aluminum boxes which we can just open, and then we see inside a sample holder, and in reality there's also a coil to apply a magnetic field and some cables to connect the sample to the outside world. And when we open this sample holder here, then we see the actual sample with the 2 feed lines, one from the P side here and S on the other side, and the little black rectangle in the middle is the heart of our sample. This is the chip with our quantum circuit. And since this quantum circuit is very small and difficult to see on this scale, I've prepared a picture for you on a computer screen. Here you see this 5 by 2.5 millimeter circuit, and you see some structures patterned into, in this case, an aluminum or niobium metal layer. You see in particular a resonator and some control lines, and then there are some additional elements, so-called Josephson junctions and squids, which are too small to be seen here. So let's now move to Bob's side, and since our link and our cable can go through a small hole in the wall, but we cannot, we rather use the standard office doors and the hallways and go around to Bob's lab. So welcome to Bob's lab. This is where the communication partner of Alice is located. And of course, Bob is also located inside a dilution refrigerator to create the millikelvin temperatures. But here, this is closed, that you see how such a setup would look in the case of the actual experiment running. You can follow me behind this fridge. And then you see the end of the link. You see how the link comes through a hole from Alice's lab, passing through another intermediate lab, coming here into Bob's lab. And you see here the 3 superconducting coax cables sticking out here, and they will go eventually into Bob's fridge, and there we will have Bob mounted. Unfortunately, since this is closed, you could not see Bob mounted inside the fridge. For this reason, we have taken him out of his house, and we can show him to you now. So may I introduce Bob to you? This is Bob in our experiment. And for those interested more in technology, Bob consists of a so-called directional coupler. In optics, this would be a 99% reflective mirror and or transmissive, depending on which way you want to see it. And then we also need a circulator in order to direct the signal flow into a certain direction. This directional coupler actually is used to make Bob's local operation, and then the teleported state will come here out of the circulator port and can be measured on Bob's side with our standard microwave receiver and measurement setup. So this brings us to the end of this lab tour. I hope you have enjoyed it. And as a very last point, I want to give you a small outlook where we want to go at. So we have performed this teleportation experiment already inside a single fridge successfully. You can find a preprint on that on arXiv. It has been published, it has appeared on arXiv already in April. And now in the next step, in the current step, we are mounting the 2-fridge setup, and we are planning to finish this experiment this year or maybe early next year, the teleportation experiment between the 2 fridges. In the further future, we hope to extend our 2-node network, so our point-to-point network setting, with a 3rd arm into a star-type configuration to explore non-trivial network topologies. And of course, at some point, we would also like to teleport actual qubit gates, and in the far future, contribute to true quantum local area networks between superconducting quantum processors, or even in the very far-fetched future to things like quantum supercomputers. Thank you very much, and goodbye for today.